Am I audible? Am I audible? Yes. Okay, we will start our today's section, or the you can say this is the 12th lecture of this ISSS course titled Introduction to Astronomy and Astrophysics. We will start our session shortly. I guess my screen is visible. Welcome everyone for the 12th session of ISSS course Introduction to Astronomy and Astrophysics. From the last class, we have started the module M3, which is will be the module is named in the extragalactic astronomy in our course handout. And in this module, we will cover 3 lectures. Those 3 lectures will be the first lecture was in the previous class. We introduced what are the galaxies, and today's lecture will be some more information about galaxies. And from tomorrow's lecture, you can learn about what is known by the evolution of galaxies. Now, first, I will review what I was discussing in the class. So I should share the screen now. Yes. So today is the second lecture of this galaxies. Now, first I will review what are the galaxies, which we learned in the previous class. So galaxies is one of the main structure of the universe on the large scale. In the generally, when you think about the universe, it is made up with 3 content. One is the matter content, another is the dark matter content, and another is the dark energy content. So the matter content is about 4 to 5% content of the universe is made up with the normal matter. The main thing about normal matter is this normal matter interact with the gravity, mainly interact with gravity, and they have the electromagnetic interaction. And there is another type of matter that is known as dark matter, which only interact by the gravity. In the universe, around 23% of matter is the dark matter, and there is another type of content that is the dark energy. That is the main part of the universe, and it is thought that this dark energy is causing the expansion of the universe. This dark energy, what is dark energy, that is currently unknown. I guess am I audible? Okay. So this dark energy does not interact by gravity or electromagnetic force, but it is the main content of the universe. The morphological main content means the content which is not the main content, you can, or the main content means here I am trying to say the content which is the most highest fraction of the total content. Now we had seen that morphologically we can classify galaxies in 3 distinct classes. One this is the spiral galaxy, another is the elliptical galaxy, and the next type is the irregular galaxy. Here one such example of morphological classification is shown with the galaxy's image. In the left extreme side, you can see the galaxy's view of NGC 1356. It is one of the prototype spiral galaxy. This kind of spiral galaxies show flat rotating disk structure, and the spiral arms are clearly visible in such systems, and often it is believed that there is spiral arms and also there is a central bulge kind of thing in these galaxies. Generally, this galaxy is about in the 10% so the ratio of stars to gas is about 10 is to 1 for this type of galaxies, and the spiral galaxies have the high star formation rate. The spiral arms are the region of the star formation. The as this galaxies is having the current star formation, so there are massive O or B type stars are forming in this galaxy. So these galaxies are often seen in bluer color. They are seen to show the bluer colors. Here is in the middle you can see the next type of galaxy, that is the elliptical galaxy. So this are spheroidal or the ellipsoidal in shape. These galaxies have lack of gas. Gas to stellar mass ratio is very less than 0.1. These galaxies have lower star formation rate. So these galaxies have the older stellar population, and these galaxies do not contain very massive hot star. So they are devoid of the bluer color, and they are the red galaxies. And next type of galaxy you can see in this image is NGC 1427A. This galaxy has no shape like the spiral with shape or the ellipsoidal or spheroidal shape. This type of galaxy but this type of galaxy has been observed to have the moderate star formation rate, or sometimes star formation rate very comparable to the spirals also. This galaxy have the large amount of gas present. Gas to stellar mass ratio is about 1 or greater than 1 for this type of galaxies. Now this was one short review for the yesterday's class before going to today's lecture. We had seen what is the difference between the dark matter and the ordinary matter. What is the role of the dark matter in galaxy formation? That is, the dark matter helps to clump ordinary matter together, and this dark matter form a scaffolding for the galaxies to form and evolve and shaping the universe large scale structure. Now we had discussed already that what was the how the idea of extragalactic astronomy came. So this first when in the 17th century or the 18th century, there was idea that the patchy bright objects on the sky, those are seen by the then telescopes, were some objects within our own Milky Way. There until 1920 there was debate whether the spiral nebula were island universe, or they are outside our own Milky Way, or they are outside our own Milky Way or inside our Milky Way. In 1925, the astronomer named Edwin Hubble measured the distance of such one nebulae known as the Andromeda or the Andromeda galaxy, and found that this distance for that Andromeda galaxy is very much larger than the distance of than the most last distance of our own galaxy. So from that he found that there are also galaxies other than our own Milky Way. So extragalactic astronomy is the most one of the most recent fields in the history of astronomy. So extragalactic astrophysics or astronomy is about 100 years old. Now we already had discussed about the two catalogs which are often come in this extragalactic astronomy lectures. One such catalog is the Messier catalog, Messier catalog. That is something M87, M82. That kind of galaxies are within this Messier catalog. And another catalog is the NGC catalog. That is the New General Catalog, which was given by 1888 by Dreyer, which had about 8,000 objects, and this about 50% of the sources within this NGC catalog were galaxies. Now we had seen also the different types of galaxies, such as the elliptical, spiral, lenticular, ultra diffuse, interacting galaxies, and we also discussed about the shape or the of the spiral galaxies, such as the disk where the stars are forming, and the halo or bulge where the older star um, are present, and the central bulge region and the central burns region or the central bright region. Now the second thing we also discussed in the yesterday's talk, that are the Hubble's galaxy classification. Hubble gave in 1935, around that time, the Hubble provided a systematic way to classify galaxies based on their morphology. And Hubble himself proposed that there are two types of galaxies, such as elliptical galaxy and spiral galaxy, and he just oriented them in some well known or the some good sequence. The S0 was just in the middle here, and from the S0 there are galaxies evolving to SA to SC, and from SB0 the galaxies are evolving from SBA to SBB, SBBC. And then for the spheroid galaxies, he gave there in the previous, in the other direction, there is the spheroid dominates or the spheroids or the round appearance galaxies gets dominated. So this kind of Hubble tuning fork diagram serves as a fundamental framework for the modern galaxy classification system, influenced the study on galaxy evolution and formation, and from the after Hubble's tuning fork, there was a question whether this kind of sequence help us to understand the galaxy evolution, how the galaxy gets transformed from elliptical type to spiral type, or in spiral type galaxy transformed to elliptical type. So this thing came after giving this idea came after, or these questions came after Hubble's tuning fork diagram. Now we had discussed some other types of galaxies, such as the very low mass, that is the 10 to the power 7 to 10 to the power 10 solar mass galaxies, where the luminosity is very low. This luminosity is about 10 to the power 6 to 10 to the power 10 solar luminosity, and those galaxies within some 5 kiloparsec distance, and those are dark matter dominated galaxies known as the dwarf galaxies. It has been observed that the majority of galaxies are the dwarf galaxies. They have very low surface brightness, so very high redshift dwarf galaxies we cannot detect. So dwarf galaxies are very good tool to study in the low redshift universe. They are very good tool to study how the galaxies get formed by merger, or what is the formation history of galaxy, as they are very abundant. Now here we discussed about the tidal stream which is observed in our Milky Way. This tidal stream is believed to be due to the Sagittarius dwarf galaxy, which was orbiting the Milky Way for billion of years. As it was orbiting, it gradually got captured due to the gravitational effect of the Milky Way, or the gravitational potential of the Milky Way, and some of these galaxies stars or the galaxies gas, those got ejected and formed a tidal stream kind of structure around our own Milky Way. And the recent satellite, the Gaia satellite, has detected such tidal stream, many such tidal stream around Milky Way. So this confirms that yes, there are dwarf galaxies surrounding us also, and uh, they do interact with our own Milky Way over the course of time. Now we had also discussed yesterday how the galaxies are grouped together. We discussed about the galaxy groups, that are the mainly of less 110 to uh, 30 or few dozen of galaxies per group. And next we discussed about the galaxies cluster, which are about 100 to 1000 number of galaxies, and it has been told to note it down that the elliptical galaxies are much more found in the huge cluster, within the huge cluster. The next thing, which is the main thing from the yesterday and also the main thing to discuss for today, is we will discuss about different kinds of galaxies. And first we will tell our student that how to extract some informations about the galaxies from trusted source in the astronomy. So now we discussed different type of galaxies, such as the bird spiral galaxy. This is one spiral kind of galaxy, but in the central region of this galaxy you can see there is a the light is getting concentrated like a bar kind of thing, bar kind or a bar kind of structure. One such galaxy is NGC 1300. The next kind of galaxy we discussed is lopsided galaxy, where some other nearby galaxies is tugging the disks of this galaxy. Such example of galaxy is NGC 2276. And this galaxy, we will see some feature of this galaxy and also its neighbor in our Aladdin web browser. And next we discussed about the shell galaxy, the grand design galaxy, the flocculent spiral galaxy, and the and maybe we ended our discussion with the ring galaxy. So what is the ring galaxy? We will start today with the ring galaxy. Ring galaxy has a circle-like appearance. The ring galaxy contains one star formation ring, and the ring contains many massive, relatively young blue stars, which are extremely bright. The central region of this galaxy contains relatively little luminous matter. It is believed that the ring galaxies are formed when one smaller galaxy passes through the center of the larger galaxy. The next type of galaxy what we will see today is the Seeger galaxy. When you get the term Seeger galaxy, the M82 is known as Seeger galaxy because of this is the appearance of M82. It has been seen that this M82 galaxy it's a starburst galaxy, and it shines brightly in the infrared wavelength, and it has very high star formation activity. This Seeger galaxy experience a gravitational interaction with its neighbor known as M81, and which is causing it to have extraordinarily high amount of star formation or a starburst. This is one image of the Seeger galaxy or aka M82 galaxy. You can see here the sugar-like shape of the disks, and also some infrared light coming in this out in this galaxy. Here is the Hubble image. In the left side is the Hubble image, which is the most detailed view of M82 score that was captured by Hubble. And this isolates the light from the glowing gas cloud, while blocking out the much of the starlight. This image shows the light is emitted by sulfur in red, visible and ultraviolet light from oxygen in green, blue, respectively, and light from hydrogen in cyan. We will come back to Cigar Galaxy later on, but now we will introduce you another galaxy, that is the Cutwell Galaxy. Now, this is a one such great image. Maybe you all have encountered this image in the GWST's web page. That this Cutwell Galaxy has a Cutwell-like appearance, and this is the image of the Cutwell and its companions from the Webb's near-infrared camera and the mid-infrared camera, which reveals the details that are difficult to see in the individual images alone. This galaxy is formed as a result of high-speed collision that occurred about 400 million years ago. This Cutwell or the ring-like galaxies are believed to be formed when there was some high-speed collision with the other neighbor galaxy. This Cutwell you can see is composed of the two rings, a brighter inner ring and a brighter inner ring you can see, and a outer ring which is also a colorful ring. Both the rings are believed to be expanding from the center of collision like a shock wave. This is the image of the Cutwell Galaxy. We will see how to find the spectra or that is the flux versus frequency, or how to find the array, or how to find distance of this Cutwell Galaxy in the reliable way using the NED browser. The next type of galaxy what we will discuss in this course are is comet galaxy. So this yes, one thing to mention, this comet galaxy or the Cutwell Galaxy or the Cigar Galaxy, those are not the type of galaxy, those are only the nickname of few galaxies. Those nicknames are given based on their appearance. Those are not a type of galaxy. Just keep this in your mind. Yes, thank you, you mentioned it. Because this Cigar Galaxy, this M82's nickname is Cigar Galaxy. Here is the Cutwell Galaxy. Here this galaxy has also some Mason name or other identifier names. With what we will see which galaxy's name is in other catalog, Mason catalog or NGC catalog. What is the name of this Cutwell Galaxy? Other nicknamed our one other galaxy we will see is the Comet Galaxy. So now this, what is the Comet Galaxy? In galaxy cluster we roughly see two type of galaxies. One is the gas poor elliptical galaxy. Those are found near the center of the galaxy clusters, while the spiral galaxies where the star-forming gas is present is often found in the periphery region or the circumstances or the less crowded circumstances of the cluster. While looking at the galaxy cluster Hubble 2667, here is one of the view of the Hubble 2667 galaxy cluster. This is one of the Hubble Space Telescope view of this Hubble 2667 cluster. You can find one galaxy. This is some odd looking galaxy. This is odd looking galaxy, some odd looking spiral that flows through the cluster after being accelerated, flows through the cluster after being accelerated to at least 3.5 million km per hour by the enormous combined gravity of the cluster's dark matter and the hot gas and the other 100 members of the galaxies. As it speeds through, it is believed, so when they were studying this Abell, 2667 cluster, they found one odd looking galaxy, just like a comet like appearance, just a tail kind of thing you can see in the full high resolution image, HS image. So this galaxy they named the Comet Galaxy. It is believed that the Comet Galaxy is plowing through the cluster and being accelerated at the speed of 3.5 million km per hour, with the effect of the cluster's dark matter potential or the hot gas and the gravitational effect of other hundreds of members present in this Abell 2667 cluster. As this galaxy is speeding through the cluster, it rams into the hot gas that is present in the cluster. Gas and stars are pulled away by the gravitational tidal force exerted by the cluster. So the as just the forces exerted by our moon and sun pull our oceans. It has an extended stream of bright blue knots and diffuse whips of young stars, which combination formation and evolution has been driven by both cluster's tidal force and the mechanism called the ram pressure stripping. From such stripping thing, this some gas and the stars get stripped by the gravitational effect of the whole cluster. The main thing is this for the Comet Galaxy. Here it has been found that Abell 2667's hot gas is composed of charged particle, where the temperature is about 10 to 100 million degree. During the ram pressure stripping or the stripping of gas, the charged particles strip and push away the infalling galaxy's gas, just as the solar wind of charged particles pushes the ionized gas away from the comet to create the such gas tail like appearance. For this reason, this galaxy in the Abell 2667 cluster has been named as the Comet Galaxy. So Comet Galaxy is one in one sentence you can remember that Comet Galaxy is a galaxy that is present within Abell 2667 galaxy cluster, and this galaxy some amount of stars and the gas of this galaxy gets stripped by the gravity of the whole cluster. Here is one image of the HS image of the Abell 2667 cluster. We will see how this cluster look at the different wavelength. The next galaxy is the Fireworks Galaxy. So this MGC 6946, this galaxy is known as the Fireworks Galaxy. So NIS Fireworks Galaxy, it is an intermediate Fireworks Galaxy that is located about 25 million light years away from the in the constellation Cepheus. It has been named as the Fireworks Galaxy because this galaxy has the many spiral arms, and also this spiral arms show unusually high supernova rate, with at least 10 supernova recorded in the per century and far exceeding the typical rate for the galaxy of its typical size. The galaxy's high star formation activity, likely to be influenced by the nearby galaxies, contributes its interaction by the nearby galaxies, and this interaction contributes to the explosive stellar events occurring in this NGC 6946. The rich blue color and the intricate spiral arm makes a stunning example of actively evolving galaxy. The next type of object or the next type of galaxy we will introduce to you is the hoax object. The Hawk's object is a rare and the nearly perfect ring galaxy that is located about 600 million light years away in the constellation Serpens. This Hawk's object consists of a bright central core surrounded by a nearly circular ring of young, hot blue stars with large gap of seemingly empty space between them. This galaxy's unusual structure is not fully understood, with theories suggesting it to form through gravitational interactions or galaxy collision or by some other unique internal dynamics. This object was first discovered in 1950, and this object remains one of the striking and mysterious example of the ring kind galaxy. One thing we will see how the one thing you can see how the Hawk's object looks at different wavelength. Whether this Hawk's object is looks same in optical and infrared or in radio, using some services of this NED or other services which were what we introduced in the last classes. The next object is the male object. The male object is an interacting galaxy. This system is located about 450 million light years away from Earth, and this is within the Ursa Major constellation. This male object consists of two colliding galaxies, with the galaxies creating a bright elongated structure with prominent tidal tails. The intense gravitational interaction has triggered a burst of star formation, making it a classic example of merger in progress. This galaxy were discovered by Mail and an astronomer, and this system provides an insight into the galaxy evolution, that two galaxies can get merged and form such great looking structure in the sky. And also you can see that the two galaxies there are in such structure, there are two galaxies are present. You confirm this by because this has different color and this has different color. Just this systems give you idea that galaxies are not one just a standard body what is within the sky. It will remain as it is as now or about few billion years. Above within some billion years or alien years, this galaxy can collide with its neighbor and form such kind of great structure in the galaxy in the sky. The next galaxy I will tell you. Is the Black Eye Galaxy. M64, a spiral galaxy, is known as Black Eye Galaxy, and this galaxy is located about 17 million light years away from Earth, and this is within constellation Coma Berenices. This Black Eye Galaxy is famous for its striking dark dust band obscuring the part of its bright core, resembling a black eye. This galaxy has an unusual counter-rotating structure, where its inner and the outer region rotate in opposite direction, likely due to a post-merger with the other smaller galaxy in the vicinity of it. The ongoing internal interactions fuel the star formation and give M64 its distinctive appearance. This is the view of the M64 Aka Black Eye Galaxy from the Hubble Space Telescope, and this is a spiral galaxy located about 17 million light years away, and this galaxy is referred as the Evil Eye Galaxy or the Black Eye because you can see here a dark band of dust that sweeps across the one side of its bright nucleus at the center. So at the center there is a bright nucleus, and around it there is a dust cloud, which makes its appearance like a alveoli. So M64 is known to astronomers for its strange internal motion. So in this today's class, we are discussing few galaxies which are given nicknames based on their morphology or appearance. Based on its morphology, M82 is called the Cigar galaxy. There is also, based on morphology, there is Cutwell galaxy. There is, based on morphology, there is Comet galaxy, that is within Hubble 2667 galaxy cluster. Based on morphology, NGC 6946 galaxy is called the Fireworks galaxy. There is also Hoax object, that is a one circular galaxy in the sky. Based on morphology, there is M64 is known as the Black Eye or Evil Eye galaxy. Based on morphology, NGC 4038 and NGC 4093 are known as antenna galaxy. The antenna galaxies are a pair of interacting galaxies which are about 16 million light years away and situated in the constellation Corvus. They are in the late stage of cosmic collision, produce the massive star formation region, and long curved tidal tail resembling an insect antenna is observed for these galaxies. This galaxy is one of the prototype example for irregular galaxy. This galaxy is believed that the galactic merger has led the formation of 1,000 new stars in this galaxy stars and new star clusters in these galaxies, and some of this will eventually become the globular cluster. As a preview of our own Milky Way's future collision with Andromeda, the antenna galaxies offered the glimpse of fate of two colliding galaxies. So this NGC 4038 and 4039, these two galaxies are merging, and these galaxies are based on their appearance like resembling insects antenna. These galaxies are called antenna galaxy pair. So like this, UGC 10, 2 and 4, this galaxy is known as the tadpole galaxy because like tadpole like appearance. You can see this tadpole like pole here in this galaxy, and this tail contains numerous bright blue star clusters created during interaction. The tadpole galaxy serves as an example of how galaxy mergers and interaction shape the cosmic structure over the time. So until now we had discussed few specific galaxy which have good nickname. Now we will discuss another type of galaxy. This is the galaxy type. This is galaxy type, and those were specific galaxy with great nickname or very good nickname. So this antenna were NGC 4038, that is the antenna galaxy, and UGC 10, 2 and 4, this is known as the tadpole galaxy. The next we will discuss few type of galaxy. This two types of galaxy. One is the H-on spiral galaxy and another is the polar ring type galaxy. H-on spiral galaxy. This type of spiral galaxies are the spiral galaxies when they are viewed from the side, they appear like the thin flat dish and the central bulge become prominent. One such example of is M104, also known as the Sombredo galaxy, which appears as a bright glowing disks with a dark dust lens. Observing galaxies in this orientation helps us to study the galactic structure, explore the halo dark matter distribution, and the star formation in the disk itself. The edge on view also reveals that how interstellar dust affects the appearance of galaxies by blocking or scattering light. So here is one example of the uh, of such H-on spiral galaxy, that is the sombrero galaxy. This sombrero means the Mexican is a sombrero is a type of Mexican hat. This look like a broad brimmed Mexican hat like the sombrero galaxy. This galaxy in the Messier catalog, this galaxy is known as M104. This is the spiral galaxy seen from its side, and you are getting an H on view. The center of M107 is thought to be hold a thought to be host as a massive black hole. The last type of galaxy what we will introduce in this course is the polar ring type galaxy. A polar ring type galaxy are the rare type of galaxies where the ring of stars, gas, and the dust orbit perpendicularly to the main galactic disk. These rings are believed to form through the galactic mergers or the accretion of materials from the passing galaxy. A well-known example of polar ring type galaxy is NGC 4650e, which exhibits a bright central core with a large, nearly perpendicular ring. This study of polar ring galaxy provides us insight into how the dark matter is distributed within the galaxy and how the galaxy formation dynamics occurs. Two examples of the polar ring galaxies are given in this slide. One galaxy is NGC 660, that is the new general within new general catalog, and another galaxy is NGC 4650a, which is also a polar kind of galaxy. Now, today we will start our hands-on session, and discuss some multi-wavelength view of our Milky Way in the today's lecture. So before going to today's lecture or going forward to today's other slide, we just recap what we have learned till now. So today we had introduced also today and the day before we had known that about three type of galaxy, or the three major type of galaxy. Three major types of galaxies are spiral, elliptical, or irregular. The spiral, you can see the spiral is named because it has the spiral arms, which are the star forming region in this galaxy. And ellipticals are named because they are ellipsoidal or spheroidal in shape. And the irregular galaxy, this is named because they have no shape. These are three major type of galaxies. Other major type of galaxy is lenticular type of galaxy, where you can see this spiral galaxy, some H-on view of the spiral galaxy. This is known as the lenticular galaxy. And also we now discussed few interesting galaxies. Today's lecture were mainly on the few interesting galaxies, such as the bird spiral galaxy. We had given one example of bird spiral, that is the NGC 1300. You can from the image itself you can see the bird structure on the central region and also the spiral arms. Other type of galaxy we showed, that is the lopsided spiral, where you can see some amount of matter of this galaxy has been pulled in one region, and other part there is less amount of matter. These types of galaxies are known as lopsided spiral galaxy. NGC 2276 are one example of such galaxy. The next type of galaxies which we introduced are the shell galaxies. Shell galaxies are elliptical galaxy. Those are the shell-like structure which does not observed in the spiral galaxies. This structure are thought to be developed when the larger galaxy absorbs smaller companion galaxy. That is, as the two galaxy center approaches, they start to oscillate about a central point, and the oscillation creates some gravitational ripples, like the wave ripples, not the gravitational wave, just some gravitational ripples of gas forming the shells of stars, and the similar ripples spreading on water. No, there is nothing called the gravitational wave ripple. This is not the gravitational wave, is the other thing. We will not discuss that, or that is beyond our scope in this course. This is the just a one ripple kind of thing you can see in such shell type of elliptical galaxies. So now, for now, I will tell you that shell type of galaxies are those elliptical galaxy which have some ripples kind of region. If you see image of this cell galaxies, you can see such ripples or the ripples of the shells of star formation. The next type of galaxies we introduced the grand design spiral, such as M81, where you can see the clearly defined spiral arm and the central bulge region and the central bulge region. The next type of galaxy is the flocculent spiral. Those are different. So the flocculent spiral, grand design spiral, lopsided spiral, bird spiral, those are, you can say, those are the subtype of spiral galaxy based on how the central bulge or the how the outside spiral arms are seen in the picture or the image or you can say in the optical image how the spiral arms look. Based on that, the spiral galaxies are differentiated into different subcategories, such as the grand spiral, lopsided spiral, bird spiral, grand design spiral, flocculent spiral. A flocculent spiral galaxy is a spiral galaxy which has this patchy, discontinuous spiral arms in the circumsphere. So this galaxy often have a chaotic and the fluffy appearance due to their irregular distribution of star forming region. In our Milky Way also we see some flocculent kind of characteristics. Many flocculent spirals are low massive galaxy, and they are rich in gas continuing to form stars over longer period. The next type of galaxies are the ring galaxies. We will not discuss any such example of the ring galaxy, but I will tell our students to check what are the examples of the ring galaxy. This ring is the ring of star formation. So today's lecture discussed about few galaxies which are few particular galaxies which are given the good nickname, these galaxies are given this nickname based on their morphology. So based on morphology, I have M82 is called the Seeger galaxy. But there is another galaxy named the Cutwell galaxy. There is another galaxy in Abell 2667 galaxy cluster named as the Comet galaxy. We discussed about NGC 6946 also, which is known as the Fireworks galaxy. We discussed about the hoax object, male object, M64, which is known as the Black Eye galaxy. NGC 4038 and 4039, which are the interacting galaxy system known as antenna galaxy due to their morphology. And NGC 10 214, which is known as the Tadpole galaxy. At the last of this today's lecture, we discussed about the two type of galaxy, such as other type of galaxy. One is the Echon type spiral galaxy, and next is the polar ring type galaxy. And given their example, you can see. Now, one thing in the today's session, we will see how to access the image of these galaxies and how to check how far they are from the earth, or how their emission looks from the very trusted source. So for that, I will tell you to use the NED. You can search, I guess my screen is visible. Okay. So go to the Google and just search NED Astronomy. So this NED is the NASA or IPAC extragalactic database. So you can learn what is NED. This is the most trusted database which is often used by the astronomy practitioners for looking the different properties of the galaxies, or downloading image of the galaxies, or the downloading the spectral energy distribution of the galaxies. And you can just check what is the overview of NED. So NED was aimed to capture the most reliable senses of the extragalactic objects and provides the essential data to facilitate the astrophysics research and exploration. Here you can see how you can use NED and what thing you can search with the NED by this thing. The objects can be queried by name, near name, or near position, or reference code. Galaxy samples can be constructed by parameter constraints on sky area, redshift, flux density, object type, surveillance, or by galaxy classification attributes. And you can check the user guide of NED. But if you are very lazy like me, you can just check different drop down list and first look what is their functionality. So first go to the search object and by name. I will just show you then how to search the objects which have nickname, or the objects, or the extragalactic objects which have nickname from the NED archive. So first we will search for the Seeger galaxy and see what is the array disk of the Seeger galaxy, what is the redshift of the Seeger galaxy, that is where in the sky this Seeger galaxy is located, or what is the redshift, means the how far this galaxy is from you to or Earth. Now the redshift 0 when the Earth is redshift 0, and as you move very far, the redshift gets increased. So far the objects, the redshift is high. Yes, we have not introduced the idea of redshift yet. Maybe we will not introduce this today or in this lecture of galaxy, but I will say you to concentrate the thing that if the redshift is very high, then the objects are very far away from us. The main outline for today's lecture was to how to access the information of different well-known galaxies such as Seeger, such as the Cutwell, such as the Fireworks, such as the Hoax object. Can we search them on the, we will see, can we search them with their name in NED. So now I will just write Seeger. I'm searching by name. Search in progress. It will take some time. I have not tested yet whether this works or not works. Yes, for the Seeger Galaxy it is working. So NED is storing data for Seeger Galaxy or the Messier 082. Here is the cross ID, that is the cross identification for this M82 galaxy. This M82 is known, Seeger Galaxy is known as, have different 91 names, such as you can see here: Messier 82, NGC 3034, ARP 337, PRC D13. These are different catalogs and these are their ID. Third Cambridge 3C catalog, the 3C is third Cambridge catalog, fourth Cambridge catalog. These are also radio source. Here one thing, here you can say, also this is has the within the SDSS catalog. Array, deck, and this array, deck, hour, minute, second, and degree, minute, second. This kind of nomenclature they have given. SDSS, IRAS, RBS. This is also within NVSS survey, Villas survey. W map also have that. RX, Swift survey, Gamma survey, radio source also, X-ray source. The main thing to show you this, that if you just search for this M82 or the Seeger Galaxy, you will see that it has been detected in different web band also, other than optical. So other than optical, it has the X-ray detection, radio detection, gamma detection. IRAS detection means the infrared. This IRAS was infrared detection also. Yes, infrared source, you can say. Infrared source. Sorry, irregular source, I guess it. This is irregular source. I have to confirm. So here you can just see what is the position of this object in the sky. That is with this array and deck. Array is 9 hours 55 minutes 52.9 second, and deck is 69 degree 40 minutes 46.14 second, or in the degree array deck is given. Also position angle is 0. I will not get in the galactic coordinate, its longitude and latitude is given, and it is very near to us. Its redshift has been measured also. I will tell you to measure, to see the redshift. Here is the redshift is given, and the distance is about 3.8 plus minus 3.8 plus minus 0.1 megaparsec. Its diameter is also given. Galactic foreground, galactic extinction at that direction is also mentioned. Here is the cross ID or the other names which has been given to this source. Here is the coordinate. Here is the redshift. distance, classification, galactic extinction, notes, spectra, here is the spectra of this galaxy. You can download it from here itself. Here are different study which have taken the this spectra of this object, and this you can just see what is the most recent spectra that has been within NED archive for this object. I'm guessing here 2001 getting one 2016 spectra which is taken by the Herschel telescope. And which line it is taking? Carbon 2158 micrometer line it is taking. Another thing, the best thing to check is what is the view of this galaxy in different wavelength. So optical, this shape is here. X-ray also, this has some it has some great shape. You can see this which telescope has taken this image. Here is the Einstein telescope's view of this galaxy. Here is also another Einstein telescope's view of this galaxy. Here is the Rosette, another X-ray view of this galaxy. 100, this just increase it. I want to show you the radio view of this galaxy, if that is available. Far infrared millimeter radio. This is the radio view of this galaxy. Sorry. This is the radio view of Seeger galaxy taken by VLA telescope. This data was very old. And in this notes you can check when this image was taken. This image was in 1987 image. I could not find any recent image. I have to just check. Information, spectra, band, lambda, this is wavelength, lambda angstrom, band, field of view, resolution. Sorry. One thing you can just check the image resolution in arcsecond and try to go for the more finer resolution. 0.4 gigahertz. This is the 2 arcsecond for image. It should show. Field of view 7.3 degree. Here this hub mile VLA These are name of different radio telescopes. WSRT is also a radio telescope. IRAM is also radio observation. Now we will go to another next type of galaxy, that is the known as antenna galaxy, that is NGC 4038. Now we will do one thing, just one quick thing. I will just write ANTENNA, antenna. Let's check if antenna galaxy is within this list. Yes, antenna galaxy is also within this NED web page, or the NED storage, you can say. You can get the overview of the antenna galaxy, that is here the two what are the different names of the antenna galaxy with the different galaxy survey service, such as the service such as it is seen by the IDAS. So this is given the IDAS 1835 1836. 2 mass survey has also seen this galaxy. So this galaxy is at redshift 0.005, and object type you can see here, the galaxy pair, morphology, appearance of fission. This classification is based on this 1966 paper. Other H2 region is also found in these galaxies. This I will not discuss. So just you can get the images of this galaxy. I will show you some. Let's look how antenna galaxy looks in radio. Mid infrared. Here is one view of antenna galaxy in radio. This is the radio view of antenna galaxy. You can increase field of view, decrease field of view, you can just see. Zoom, original size, zoom image to fit the entire frame. Color drop, change color double. Change color. Change scale. You can just play and see if you what structure you are seeing in this image. The main focus of the main thing, take home thing for today's lecture is you can search for this galaxies from the NED browser itself and get idea about what is the distance of this galaxy in the megaparsec, what is the photometry or the spectra for this object, or how this galaxy or how this some galaxy looks different in different wave band. Now we will you can just play with some of this galaxy, or if the time permits I will show you few examples of this NED browser also. Now I should go forward, because if I try to check this NED example I cannot end the whole galaxy lecture. Now I should view slideshow. Now we will start our session, start the few slides on the multi-wavelength view of our own Milky Way. So in all sky view uh, from the earth show that the Milky Way is a band of light, sometimes dusty, or the clouds obscure our view to the galactic center, and this gas cloud absorbs the light emitted from the stars. This gas cloud absorbs the light in the visible light. This gas cloud is known as the interstellar medium, and this interstellar medium is the main fuel for forming the new stars in the galaxy. All sky maps seen from the Earth view is the view of the Milky Way seen from the inside. Milky Way is composed of millions of stars, much gas and dust. If you can see the Milky Way in other web bands, or that is the web bands other than our optical, 400 nanometer to 800 nanometer approx, you can get the spectacular view of our Milky Way. So now one such Milky Way's galactic view of Milky Way's galactic plane at different frequency is given you in this slide. I will go to each of these dots and make you feel why you have to view our own galaxy at different wavelength. So first we will show you the view of our own Milky Way in two different radio frequency. That is the radio frequency, the lower radio frequency at 4808 megahertz, 408 megahertz, and another is the 1.4 gigahertz, that is H1 line frequency. So what the radio continuum observation at 408 megahertz is telling. Intensity of the radio continuum happens from the high energy charged particle present in our Milky Way. With the survey of the ground-based radio telescope like the Jocelyn Bell Mark 1 or Mark IA, Born 100 meter and Perkins 64 meter, 408 megahertz map of the Milky Way has been derived, what you have seen in this figure. At this frequency, most of the emission is coming from the electrons moving through the interstellar magnetic field at nearly speed of light. Shock waves from the supernova explosion accelerates electrons to such high speed, and these electrons produce specifically intense radiation near to the source where they originate. Emission of the supernova remnant near Cassiopeia A at near 110 latitude is so intense that the diffraction pattern of the support legs of our radio receiver on the telescope is visible as a cross shape. We will not discuss this last sentence because this is beyond our discussion here. So one thing to keep in the mind that the radio emission or the low frequency radio emission is larger near the place where it has been originated. Here is the 51 arc minute map, 50 arc minute resolution map of map at 408 megahertz. This is the radio continuum map at 408 megahertz. The next map is about at 1.4 gigahertz map, that is with the angular resolution of 45 to 60 arc minute. Atomic hydrogen, this is the atomic hydrogen map. The column density of atomic hydrogen derive of the assumption of optically thin emission from the radio surface of 21 centimeter transition of hydrogen. The 21 centimeter emission traces the cold and the warm interstellar medium, which on the larger scale is organized into the diffuse clouds of gas and dust that have the sizes of up to 100 of light year. Most of the images are based on the Leiden-Duigno survey of galactic neutral hydrogen using uh, Duiglo 25-meter radio telescope, and the data is corrected for the cyclone contamination. All the slides has been taken from this website. If you wish to visit, you can visit and get the you can visit for your own this website for your own reference and check uh, the content of the slides. The next emission mechanism is the radio continuum mechanism, or the next emission map is the radio continuum map at 2.4 to 2.7 gigahertz. So, intensity of radio continuum emission from hot ionized gas and high energy electrons in the Milky Way from the surface of in the Milky Way seen is traced in this map. This map has been made from the surface with the 100-meter Bond telescope and Parker 64-meter radio telescope. Unlike most other views of our own galaxy presented here, this data is extended only to the latitude of 5 degree from the galactic plane. The majority of light emissions seen in this image are from the hot ionized region, or that is produced by the region where the very energetic high energy electrons are moving in the magnetic field. The higher resolution of this image is compared to the previous 408 megahertz image shows the galactic objects in the more detail. Note that the bright reach of the galactic radio emission appearing predominantly in 408 megahertz image has been subtracted here in order to show the galactic feature and the objects more clearly. So, the 2.4 to 2.7 gigahertz radio continuum map traces the hot ionized gas and the high energy electrons in the Milky Way, and this map is made with the two telescopes, the Bond 100-meter telescope and the Parker 64-meter radio telescope, with the angular resolution of 10.4 arcminute, and this map is within the galactic plane 5 degree. The next type of emission what we get from the Milky Way, the molecular hydrogen emission. The Coulomb density of the molecular form of hydrogen can be inferred from the intensity of the 1,0 spectral line transition of carbon monoxide, and this is taken as a standard structure of the cold dense bud of interstellar medium. Such cold gas is concentrated in the spiral arms of the galaxy, and these regions are known as the molecular cloud. This molecular clouds are the site of the star formation. Because they are cold, here the gas can collapse. The molecular gas has predominantly hydrogen, but hydrogen is difficult to detect directly at the interstellar conditions present there, and the carbon monoxide is the second abundant molecule after the hydrogen, so it is observed as a surrogate. The Coulomb densities are derived on the assumption of constant proportionality between a constant of proportionality between the Coulomb density of hydrogen and the intensity of the carbon monoxide emission. So the molecular hydrogen maps are met at the 115 gigahertz, and this map is of the 30 arcminute resolution. This is from the ALMA and the IDAM, both two telescope. So until now we have discussed the emission from our own Milky Way in 4 different wave band. that is the radio contain the low frequency radio, that is the 408 megahertz, 408 megahertz radio, and atomic hydrogen, that is the 1.4 gigahertz radio emission, and another is the radio continuum or the high energy radio, or that is 2.7 to 2.7 gigahertz. And next we discussed about the molecular hydrogen emission, that is 115 gigahertz, that is for the made for the spectral line transition of the carbon monoxide molecule, that can be made for the spectral transition of the carbon monoxide molecule. Now we will see how our galaxy looks in infrared. So composite, mid and the far infrared intensity are observed with the satellite known as the IDAS satellite. IDAS detects emission in 12, 60 and 100 micrometer wave bands. These images are encoded in the blue, green and red color respectively. Most of the emission detected is thermal from the interstellar dust formed by the absorbed starlight, including the star forming regions embedded in the star forming clouds. The display here is a mosaic of the IRA Sky Survey Atlas images and the emission from the interplanetary dust in the solar system, that is the zodiacal emission, was modeled and subtracted and produced to in order to produce such atlas image. So this are the images at the frequency 3 into 10 to the power 3 to 25 into 10 to the power 3 gigahertz, and this are the images at the angular resolution of 5 arc minute. The mid infrared image is the WISE image, and the near infrared image is the TUMAS image. So WISE, another infrared mission, which was within some 2000, to 2010, that time imaged our galaxy in the band of the 6.8 micrometer to 10.8 micrometer. So here the WISE view of our Milky Way has been shown. The mid-infrared emission also is observed by the mid-infrared emission is as well observed by the SPIRIT instrument, just like WISE instrument. The most of the mid-infrared catches the diffuse emission in this band, that is coming from the complex molecules called the polyaromatic hydrocarbons, which are commonly found both in the coal and the interstellar clouds, and the red giant stars, planetary nebula, massive stars are so young that they remain deeply embedded in their parental molecular gas cloud, produce multitude of small bright spots seen here in the mid-infrared image. Unlike most of the other map, this map is only 5 degrees above and below the galactic plane. So this map is the WISE map is about 6.5 arc minute resolution, and the near infrared, this is the TUMAS image, and this has been this you can see here is also the infrared emission has been detected in this image. The next is the optical X-ray gamma ray emission. We will not discuss this emissions today. We will discuss those the next day. Yes, we should discuss those, I guess, because this will complete this session. Yes, optical, here is the optical image and the 1 arc minute at the arc minute resolution. Intensity of the visible light from the photographic survey can be seen here at the bottom. Due to the strong obscuring effect of the interstellar dust, the light coming primarily from the stars within a few thousand light year of the sun or nearby the scale of the Milky Way is seen. The widespread bright and the red regions are produced by glowing low density gas. The dark patches are due to the absorbing clouds of gas and dust, which are evident in the molecular hydrogen and the infrared maps as the emission region. Stars differ from one another in their color, mass, and size, and also the luminosity. Interstellar dust scatters blue lights preferentially, redden the starlight, sometimes relative to its true color, and produce diffuse bluish glow. This scattering as well as absorption of some of the light by dust also leaves the light diminished in brightness. The panorama was assembled from the 16 wide angle photographs taken by Dr. Axel Millinger using standard 35mm camera and the color negative film. The exposures were met between July 1997 and January 1999 at in the sites in US, Africa, and Germany. This image processing and mosaicing procedures are described in the document site given link in this website. This all discussion is taken about the Milky Way's galactic plane has been taken from this website, I must say, and thank them. And next type of thing is the X-ray view of our own Milky Way. Here is the X-ray view of our own Milky Way that is taken by the satellite rosette at the frequency 62 to 60 into 10 to the power 6 gigahertz and with the angular resolution of 115 arc minute. This in the Milky Way, extended soft X-ray emission is detected from the hot shocked gas. At the lower energy, especially the interstellar medium strongly absorbs the X-ray, and the cold clouds of interstellar gas is seen as the shadows against the background of X-ray emission. Color variation in this image indicates the absorption of the temperature variation in the emitting region. The black region indicates here the gap in the rosette survey. The next kind of emission is the highest frequency emission, that is the gamma ray emission, that is over the frequency of 10 to the power 13 2 into 10 to the power 13 gigahertz, and this is the 118 arc minute resolution image with the gamma ray survey with the gamma ray survey Compton Gamma Ray Observatory, and the instrument is IGRIT or the Energetic Gamma Ray Experimental Telescope. This image includes all the photons with energy greater than 300 megaelectron volt. As this extreme energy, most of the celestial gamma ray originates in the collision of cosmic rays with hydrogen nuclei in interstellar cloud. The bright compact sources near the galactic latitude between 180, 195 and 265 indicate high energy phenomena associated with Crab, Geminga and Vela pulsar respectively. Frequencies greater than at the 2.4 10 to the power 13 gigahertz. We will just see tomorrow that what is the phenomena, how the high energy phenomena with Crab, Geminga and Vela pulsars vary in this galactic plane. Here is the thing. Crab, Geminga and Vela, these three pulsars which today we will not discuss. Tomorrow we will start from the Milky Way's view. We just give an overview of the multi-wavelength view of Milky Way. Tomorrow we will try to complete this lecture with the rest of the part. Anyone have any question? Anyone have any question? If no, if you have do not have question, so thank you for joining. uh, I am closing the today's session, and tomorrow's session will be from the 5 p.m. to 6:30 p.m. That time. Or yes, we will try to complete these lectures on the galaxies tomorrow. So thank you for joining.